Today we're going to be talking about how to find the least common multiples of a set of numbers. This is a skill that you'll be using throughout algebra in particular, and algebra is used really in all upper level STEM classes in one way or another, which is essentially finding the smallest number that numbers go into. Somewhat trivial question for really easy to think about numbers, or relatively easy to think about numbers like 2 and 4. 2 and 4 both go into 4. Great. 2 and 3 both go into 6. Great. But if I ask you 24 and 62, that might be a little bit harder to come up with off the top of your head. So we have some machinery that we can use in order to systematically figure out whatever least common multiples we want. But before we jump straight to that, let's sort of back up and get a little bit of vocabulary and notation straight here. So for example, exponents. Exponents are used all the time as a way of us showing repeated multiplication. If, for example, we multiply 6 by itself 4 times, that could be rewritten more simply as 6 to the 4th power. In an exponent, the number that's big on the base, that's called the base. The number inside the exponent up top, I shouldn't define an exponent using the word exponent, right? But the number up top here, that's going to be your exponent. So the base tells you what is being multiplied, while the exponent says how many times we multiply. So with that in mind, I want you to pause your video and take a moment to go ahead and rewrite these expressions in exponential form or in expanded form. So in exponential form, the number being multiplied here is 4, and he is being multiplied by himself 4 times. For the second one, the number being multiplied is 5, and he is being multiplied by himself 2 times. Working the other way around, if I have 5 to the 7th, that means I have 5 times 5 times 5 times 5 times 5 times 5. This is where I sort of count to myself. I've got 1, 2, 3, 4, 5, 6 of them, times just one more 5. 5 multiplied by itself 7 times. 10 to the, which is rather long. You can see very quickly how the exponential form helps us communicate much more succinctly. 10 to the 4th would be 10 times itself 4 times. Now, I wrote this with x's, but as you get further in math, just to make sure that we don't confuse this with a variable, you may see that multiplication instead written with a dot like this. Those mean the same thing. We're going to utilize exponential forms in order to express our answers, and we're also going to have to know what the difference is between a prime and a composite number. A prime number has only the factors of one of itself. And what do we mean by factors? Factors are numbers that multiply into the number. So for example, for 2, the only numbers, and I should actually be more specific than numbers. Let's be more specific. Those would be the integers, and specifically the positive ones. So the whole numbers. That's really what we're concerned about here so far. So for example, with 2, the only whole numbers that multiply into 2 would be 1 and 2. 13, only ones that multiply in are 1 and 13. Those are prime. If it's composite, think the word compose. That means that more than one number, or really more than 2 numbers, I should say, goes into it. So for example, for 4, 1, 2, and 4 all go into it. For 6, 1, 2, 3, and 6 all go into it. Similarly, 12, 1, 2, 3, 4, 6, and 12 all go into 12. So those would be considered composite. Go ahead and pause your video and take a second to just circle what the prime numbers are. Jot those down either on paper or just in your head. So here the prime numbers would be 2, 11, 17, and 29. 9, 3 goes in, 16, 4 goes in, 8 goes in, 2 goes in, 21, both 7 and 3 also go in, 32, a whole bunch of things go in, such as 4 and 8. So all of those would not be prime, but the ones that are circled are prime. Why do we care about this? Well, prime factorization is a really helpful tool for us to find those least common multiples that we're leading up to here. So what's a prime factorization? That's where you break down a number entirely into its product of primes. So you can guys start however you want. There's one example that's written out here. I'm going to show with the same number how you can start these factor trees however you like. So if I wanted to prime factorize 36, let's say I initially just said, well, I know that 18 times 2 is 36. And 2 might have just been what I guesstimated to go just into 36 because 36 is even. Then 18 breaks down further into 9 and 2. 9 breaks down further into 3 and 3. And lo and behold, I've got the factors 2, 2, 3, and 3. So the ends of my branches are the numbers I'm going to pay attention to. These middle steps were really just there to help me think. I'm not going to pay attention to those numbers. So I've just confirmed that 36 is the same thing as 2 times 2 times 3 times 3, or written in exponential form as 2 squared times 3 squared. And that's the exact same conclusion that the written steps came to by initially breaking down into 12 and 3. So it doesn't matter how you start. All that matters is that you stop your branches as soon as you have actually reached a prime number that can't be broken down further. So let's go ahead and practice this. So I want you to pause your video and go ahead and try to factor both 24 and 72. So 24 you might have initially broken down a number of ways. I'm going to break it down into 12 and 2, and then 2 breaks down into 6 and 2, and then 6 breaks down into 3 and 2. So I'll notice here that this is equivalent to 2 times 2 times 2 times 3, or written in exponential form as 2 cubed times 3, 2 to the third power because 2 is being multiplied by itself 3 times. Similarly, for 72, I can break that into 9 times 8. 9 further breaks down to 3 and 3. 8 breaks down into 2 and 4 breaks down into 2 and 2. So this breaks down into 3 times 3 times 2 times 2 times 2, or in exponential form, 3 squared times 2 cubed. 315, this is a good example of something that maybe is a little bit harder to initially come up with. But since he ends in a 5, I do know that he is divisible by 5. So here to the side or on a calculator, but I'd encourage you to practice to the side, I'm going to long divide 315 by 5. 5 doesn't go into 3, so I'm not going to write something initially above the 3. 5 goes into 31 6 times. 6 times 5 gives me 30. 31 minus 30 gives me 1. Drop down the 5. 5 goes into 15 3 times. 3 times 5 gives me 15. 15 minus 15 is 0, so I have a remainder of 0. I've confirmed it's divisible by 5. So I can at least start my tree by saying 315 breaks down into 5 times 63. 63 further breaks down into 7 times 9. And 9 further breaks down into 3 times 3. So I've just confirmed that 315 breaks down into 5 times 7 times 3 times 3, or 5 times 7 times 3 squared. Now for the least common multiple, the reason why we care about this is it gives us another tool in our toolbox in order to find the least common multiple. And what again is the least common multiple? The least common multiple is the smallest number that is divisible by the numbers you're trying to find the least common multiple of. Or in simpler terms, is the smallest number both numbers, or all three numbers, or however many numbers you're talking about, go into. So the least common multiple of 2 and 3 is 6, because 6 is the smallest number divisible by both 2 and 3. Sort of similarly, the least common multiple of, let's say, 3 and 8, if it wasn't coming to mind, what I would just do is list off the factors of 3, 3, 6, 9, 12. If you notice, I'm just literally counting by threes. 15, 18, 21, 24. I think I'm going to stop about there. 8 would be 8, and then 16, and then 24. And oh my gosh, I just found what is their least common multiple, 24. Now, that isn't always valid. That is a valid strategy you always can do. It's just list off the factors and then identify what is the smallest number they both go into. Smallest number on your list of common multiples. Now, as you can imagine, this can get a little bit unwieldy whenever you have kind of funky numbers. Like if I asked you between 315 and 700, you'd look at me like I was crazy because you would have to guess and check for a long time until you came up with the least common multiples. So what's a more systematic way? Using prime factorization. So for that, what you do is you prime factorize each number, identify the common primes, you're going to list those once, and then identify the primes they don't have in common, add that to the list, and then multiply all those numbers together. So what do I mean by that? Well, 28, for example, you could break down to 4 and 7, 4 breaks down to 2 and 2, 36 breaks down into 6 and 6, 6 breaks down to 2 and 3, 2 and 3. So as you notice here, they've got a set of 2's in common. So I'm going to list those two 2's as is. So I've got 2 times 2 in common in their prime factorization. Or if you like from exponential form, 2 squared is what they have in common. So I list that once. Then I add them to my list what they don't have in common. So they've got a 7, not in common. They've got a pair of 3's, not in common. Or 7 and a 3 squared, if you will. And whenever I multiply all these together, I get 252 is their least common multiple. I don't think it would have been very fun to list off all the factors of 28 and all of the factors of 36 until I got there. By using prime factorization, I was able to get there more systematically. So I'm not gonna, even though you can always do the sort of list them off and then check what they have way, which I would recommend for smaller numbers, let's go ahead and practice the more systematic way. So let's say, for example, I want to find the least common multiple of 12 and 18. So I'm going to start off by just prime factorizing these guys. So 12 breaks down to 6 and 2, 6 breaks down to 3 and 2, 18 breaks down into 9 and 2, 9 breaks down to 3 and 3. Then I'm going to start noting what they have in common. So they have a 3 in common. Great. They have a 2 in common. Great. And then what do they have not in common? They don't have that 2 in common. And they don't have that 3 in common. And now I'm ready to just multiply these all together. So 3 times 2 times 2 times 3. That's going to get me 36. So their least common multiple is 36. If you prefer to see this in the exponential form, what you would have noticed is that 12 is equal to 3 times 2 squared. 18 is equal to 2 times 3 squared. So they would only have, therefore, a single 2 in common, not the full 2 squared. So you'd have 1 2 in common, 1 2 from the 2 squared not in common. And you would also have a single 3 in common, and then 1 3 from the 3 squared not in common. And you would have gotten to the same conclusion, that this least common multiple would be 36. If I want to find the least common multiple of 8 and 20, go ahead and try to use that same systematic method to find the least common multiple of 8 and 20. So for 8, that breaks down into 4 and 2, and 4 further breaks down into 2 and 2. 20 breaks down into 2 and 10 breaks down into 5 and 2. So what do they have in common? They've got 2 2's in common, so I'm going to list off 2 2's. What do they not have in common? They've got an extra 2 over here and an extra 5 over here. So this ends up equaling 40 is the least common multiple between 8 and 20. Go ahead and pause your video to see if you can find the least common multiple between 30 and 42. So 30 breaks down into 3 and 10, and then 10 breaks down into 5 and 2. 42, for whatever reason, this is always one I have to think an extra second on, but that breaks down into 6 and 7, and 6 breaks down into 2 and 3. So what is the least common multiple going to be? Well, they've got a set of 2's in common, set of 3's in common, and then they have a lonely 5 and a lonely 7. And then we're going to multiply this all together. This one's a little bit harder for me to do in my head, but that means I've got 6 times 35. You're allowed to multiply in any order. And then I'm just going to multiply this to the side. 5 times 6 is 30, carry the 3. Looks like that is 210. I got that from 6 times 3 is 18, plus a 3 gives me 21. If you haven't been pausing the video to try it yourself, do that for real this time to find what is the least common multiple of each of these sets of numbers. So for 40 and 60, we can break this down into 4 and 10 and 6 and 10. Now, if you wanted, you could actually pause here and already note they have a 10 in common. I'm still going to continue to prime factorize them out of habit, but you technically don't have to once you've already found that common factor. 10 breaks down to 5 and 2, 6 breaks down into 3 and 2, the other 10 breaks down to 5 and 2, 4 breaks down to 2 and 2. So let's get working on finding their common parts. So they've got a 2 in common, they've got another 2 in common, they have a 5 in common, and then what they don't have in common is this 2 and this 3. So I'm going to multiply all these together, so I get 2 times 2 is 4, 5 times 2 is 10, 4 times 10 is 40. It looks like 120 is their least common multiple. Now, if you have some pretty good number sense, you might have also thought, hey, the least common multiple of 4 and 6 is 12, and then I'm just multiplying these guys by 10, so can I just multiply 12 by 10? That actually does work. But the more you practice with these, the more that you'll build up that number sense. It's okay to just start off very systematic. Or just stay systematic for your whole life. There's a lot of things that in math that I just stay systematic on every time, and it never fails me. Here, for these guys, 16 breaks down to 4 and 4, further breaks down to 2 and 2 each, 24 breaks down into 12 times 2, 12 breaks down into 2 times 6, and 6 breaks down into 2 times 3. So, let's see what they got in common. They've got some 2's in common, they've got another set of 2's in common, they've got another set of 2's in common, and what they don't have in common is this 2 and this 3. So that ends up being 8 times 6, so their least common multiple is 48. And it might always be worth double checking, especially in a testing situation, that these numbers do indeed go into this number that you came up with. If they don't, you probably missed one of the branches of your factor tree, and that might be worth double checking.